So now let's talk about friction just a teeny tiny little bit. Let's just kind of think about if you've got a object like this and you're helping your buddy move, and you go ahead and you try to push on it, and you put your shoulder into it, you put your shoulder into it, you put your shoulder into it, and finally it tends to start moving. Then all of a sudden, as it's moving, then it actually seems to be much easier to push. You know what I mean? So there seems to be two types of friction. There's going to be static friction, which is going to be when things are not moving, and it seems to me that this type of friction is going to be a much larger force. And then there's also going to be kinetic friction, which is going to be when things are moving, and this is going to, well, seem a little bit easier to move, so it's going to be a smaller force due to friction. It does seem to be related to how massive an object is. The more massive an object is, the more friction there seems to be. And rougher surfaces tend to slide less easily than smooth surfaces. So think of pushing a box across some concrete versus pushing a box across ice. Rougher surfaces tend to have more friction. Now kind of what's going on right here is if we have a floor and we have a box on it, then even though the floor might appear to be smooth and the box might appear to be smooth, if we were to zoom in on a teeny tiny corner of it, or a teeny tiny slice of this interface, then we would actually find out that all objects kind of have an inherent jagginess, for lack of a better word, and how well these guys fit together is going to be representative of how much friction there is. If we were to be looking at this slice and the green slice was to be perfectly lined up with the blue slice, then we'd say that there's not going to be a lot of friction. If we were to take a look at this guy right here, and the blue guy was really jagged, and this green guy was also really jagged, and it fit in there really quite well, then right here we would say that there's going to be a lot of friction. So it's really kind of related to how bumpy or how sticky these surfaces are. So take a second and maybe ask yourself, when is friction going to occur? Okay, so you've thought about it a little bit. We know that it's going to occur with sliding objects. Actually, we know that it's going to occur in the air. We know that we can have air resistance, and we're going to talk about falling objects in a little bit. And it can also occur in water. That's why we can do things like water aerobics. So it's actually going to be all of these guys. Let's kind of take a step back and think about this problem. Now that you've thought about it a little bit, key word to watch out for is going to be a constant speed. And that tells us that the acceleration is equal to 0. So that tells us that the net force, or the sum of the forces, must be equal to 0. So as Sanjay right here pushes on the floor at a constant speed, then the force of friction must be equal to Sanjay's push. So kind of what this looks like is here we have the force due to Sanjay, and we need to balance this out perfectly by the force due to friction, so equal and opposite. Now let's kind of ask ourselves what happens if he pushes it and there's an increasing speed. And kind of what this guy is going to look like is this is going to be the force due to Sanjay, and this right here is going to be the force due to friction. So if I were to go ahead and down here draw the net force, kind of want a net force in this direction right there. Now it's going to be increasing speed, so it is going to be acceleration, and remember that force is going to be equal to mass times acceleration. So right here we need the friction to be less than Sanjay's push. The length of this arrow is much smaller than the length of this arrow. So I just want to come back and talk about falling balls for a little bit, because we're going to talk about balls falling with air resistance. And up until this point, we've assumed that there's going to be no air resistance. And so we can say that at any given time that an object's acceleration is going to be 10 meters per second. So at time is equal to 0, 1, 2, and 3, the acceleration is always going to be 10, 10, and 10. And we've already proved to ourselves that the velocity is going to be equal to the acceleration multiplied by time. So here it's going to be 10, here it's going to be 20, and here it's going to be 30. And we also know that the position, the distance that it covers, is going to be 1/2 acceleration times time squared. And we've already convinced ourselves that it should be 5, 20, and 45. Something else that we've also kind of learned is that mass does not matter. And we learned this in Chapter 2 when I did that demonstration where I jumped off the desk. You may be saying to yourself, well, let me think about this a little bit more. The more mass an object has, the more force it should feel. Now, if we were to you may be thinking to yourself, well, now that I've learned a little bit about weight and mass and how they're related, you may be thinking to yourself, wait a minute, I remember from Chapter 3 when we talked about freely falling objects that it turns out that mass did not matter in the least. But you may be thinking, okay, well, the greater the mass of an object, the more force that it should have towards Earth. So, if I've gotten this object like that, then it's got some force to it. However, the more massive it is, the smaller the tendency it has to move, so it's got more inertia. So we could have two bricks, say this one right here, and this one with twice as much mass, then, so this one's going to have some force divided by mass to give us the acceleration. Turns out that the force and the inertia are going to balance each other out perfectly. So here we're going to have 2 times the mass, 2 times the force, 2 times the mass, and we're going to have the same acceleration. So we're still going to have 10 meters per second squared. So that's kind of why when I jumped off the table, yes, I had more mass than just the ball, but I also had more inertia. So just to kind of check yourself, if we have a 5 kilogram ball and a 10 kilogram ball and we drop them from rest, then while Aristotle may say that the 10 kilogram ball should fall faster, we do know that they're going to accelerate at the same rate, which is going to be our old friend 10 meters per second squared. Now let's kind of finish off the chapter by introducing some friction into our falling objects. So let's talk about non-free fall. And this is going to be when an object falls downward through air, and it's going to experience the force due to gravity, and now it's going to experience some drag force. So right down here we have a falling rock, and it's experiencing its weight, its mass multiplied by gravity. And now we're going to have some drag to it, and we would now expect that the acceleration should not be equal to g. It should be a little bit less than g, because this guy is kind of pulling it backwards. So non-free fall is essentially going to be when we just can't neglect air resistance anymore. And air resistance is actually going to depend on 2 things. I'd highly recommend you remember this. It's going to be speed and surface area. Turns out that objects fall faster and faster and faster and faster, then the air resistance is going to be larger. So we can kind of say that the resistance is going to kind of depend on area and speed. So as speed goes up, then the resistance is also going to go up. Now, just kind of as an aside, that this could actually be proportional to velocity or velocity squared. It kind of depends on several factors, but it does depend on the speed. It also kind of depends on the area. As the area goes up, we would also expect the resistance to go up. And that's kind of why if you take a look at a skydiver, when they kind of point themselves downward, they can go really, really, really fast. But as the skydiver kind of fluffs themselves out to the side, sticks out their arms and their legs, then they're going to go slower. In this case right here, there's more area, so they're going to go slower. As this guy right here, area goes down, air resistance also goes down. So because this resistance does kind of depend on speed, it would kind of make sense that as an object falls, then it's going to fall faster and faster and faster and faster and faster, and air resistance is going to get larger and larger and larger and larger and larger, and at some point this air resistance is going to build up such that it's equal to the force due to gravity, in which case right here, if the force due to gravity is going to simply be 100 newtons, and this guy right here is going to become larger and larger and larger, and at some point it's going to be 100 newtons. And in this case right here, well, you can kind of eyeball this and say, look, there's no net force, so there should be no acceleration. This guy is in equilibrium, so we would expect the velocity not to change. Of course, we have a special name for this velocity or the speed. We call this the terminal speed or the terminal velocity, and this is just going to be essentially when the acceleration terminates, so when the acceleration is equal to 0, and that's going to be when the air resistance is equal to the force, simply in the opposite direction, and air resistance is going to be equal to the weight. Terminal velocity, same thing, it just has some direction implied. So let's just kind of think of what happens when a skydiver jumps out of a plane. So really quick, there's going to be my airplane. I know I should be an artist. And this is going to be my skydiver. Just when he or she jumps out of the plane, then they're not really moving all that fast. We even could say that their downward speed is equal to 0. So we'd expect their acceleration to be equal to 10 meters per second squared, simply because they're not falling fast enough for there to be any air resistance. So pretty much we would just have the weight, and air resistance would kind of be negligible, so it's going to be roughly 0. But as their falling speed were to increase, then air resistance is going to increase, and so the acceleration is going to be less than gravity, which is going to be less than 10. And then at some point, so I can kind of draw this guy right here, where here I have the weight, and here I've got a little bit of air resistance. Then we're going to reach the point where their weight is equal to the air resistance, and we simply would call this terminal velocity, and as long as they don't change their surface area, then they're going to fall at a constant speed. So just kind of take a second and do a little bit of math right here. If we have a 20 Newton falling object and it's going to encounter 5 newtons of air resistance, we would expect that its acceleration should be less than g, simply because the net force on this guy is going to be 15 newtons down. If a 500 Newton person were to fall at a terminal speed, so let's go ahead and put a 50 Newton person, and we know they're at terminal speed, so that tells us that the acceleration is equal to 0. Then the question is what does this force have to be equal to? It has to be exactly 50 newtons. Go ahead and pause for a second and ask yourself, as a skydiver falls faster and faster and faster, we expect air resistance to increase. And as they were to fall faster and faster and faster, what do you think would happen to the net force? I don't know about you, but I'd expect the net force to decrease. And lastly, as they fell faster and faster, what would happen to the acceleration? Now, I don't know about you all, but I would expect it to start off at 10 meters per second squared and work its way down to 0, so I would expect it to decrease. So what do we need to have free fall versus non-free fall? Well, really it kind of depends on an object's weight and the resistance. So let's just think of a coin versus a feather. And if we were to put these guys in a tube and turn the tube upside down, then I don't know about you all, but I would expect the coin to fall kind of fast, and expect the feather to do one of these numbers and work its way down to the bottom. Turns out that the feather is going to reach its terminal velocity very quickly, and it's going to fall slowly at roughly a constant speed. It's going to happen after the coin does. The coin falls very quickly because compared to its weight, the air resistance is so small, so it doesn't really build up, and the coin is going to hit the bottom much sooner than the feather. Now, of course, seeing this is believing this, so I have a quick little demo on this. And if I were to suck all the air out of a chamber, then there's not going to be any reason for the feather to feel any air resistance. It's going to be a perfect vacuum, so no air resistance means that there's not going to be any difference between the coin and the feather, and they do indeed fall together.